So, hello again, everyone, and let's start our today's training webinar with the title Accelerating Machine Learning with CUDA. Today, my goal is to provide an insight into the CUDA technology, as well as to provide an insight into some most used CUDA-based and CUDA-supported libraries used in the area of machine learning, as well as used in the area of deep learning. And therefore, I will not make the main focus on deep learning algorithms there, but as I said, I will focus on an overview of CUDA and on CUDA-based supported libraries today. The presentation webinar today will consist of two parts. Firstly, I will make an overview of CUDA architecture and programming model. Due to limited time, that given overview will be quite short, but at least to provide some basic concepts and principles of CUDA technology. And the second part will be devoted to an overview of CUDA-based libraries coming together with CUDA Toolkit or available as a separate open source or closed source projects. That is the plan for today's webinar. And let's start with an introduction. As you know, graphics processing units, or shortly GPUs, are widely used to improve execution speed of various machine and especially deep learning applications. Within the last 10 years, since the introduction of, for example, AlexNet in 2012. And today, the wide support of deep learning frameworks, including, for example, PyTorch, TensorFlow, enable rapid deployment of GPUs for modern high-level artificial intelligence algorithms, both for inferencing and for training of machine learning models. Of course, GPUs is very important part of development of advanced machine learning and deep learning models within the last 10 years, and therefore the impact is visible from both sides. From one side, GPUs can have important influence on the development of new machine learning algorithms, and in opposite, appearance and development of new machine learning algorithms have an influence on development, further development of new GPU technologies. Of course, today there exist different technological solutions in the market, not only GPUs, not only CPUs, but also more specialized solutions, including FPGAs or TPUs, for example, Google Tensor processing units, and so on. But still, GPUs are continuing to remain the most widely used accelerator technologies for machine learning tasks currently, because GPUs are a bit easier to program in comparison to FPGAs, for example. And the programmable architecture of GPUs make these technologies more useful for a wider range of applications in comparison to more specialized technological solutions. And therefore, we see the importance of GPU technology, and I would like to remind you what the GPU and GPGPU terms are by definition. As you probably, and I think you know very well, GPU is a term for graphics processing unit. And GPU, widely used term, is a short abbreviation for general purpose computing on a GPU. The history of GPUs is already quite long, at least significantly longer as the availability of GPU technology in the market. And we can look back already 50 and more years ago, when the formation of the base concepts for today's GPUs had been arised. The first experiments in the area of GPU technologies can be dated to the years since the middle of 1970s. However, the practical work and availability of more widely available solutions can be dated to the years of the middle of 1990s, when the first graphical chips appeared in the market for speed up of computer games at that time. But that was a time when the technological ground was formed for the next time period started at 2000. And the middle of 2000 is the time when the first GPUs, in the sense of today, as we are understanding what are GPUs today, that is time for appearing of GPU term and appearing of GPU technology in the market. And the year 2007 is the year when the first CUDA GPU has been published in the market, made available for a wide audience of customers. And that means that the historical length of GPU market is 15 years long. The last 10 years, as I said previously, are remarkable with the development of GPU technologies and application of GPU technology in the area of machine learning, having both influence from both sides, from algorithmical and technological sides. That is a short history of GPU technology development. If we are making some comparison between GPUs and CPUs during the 15 years history, we can see that the performance of GPUs have been increased significantly in comparison to traditional CPU technologies, and the difference between the relative performance of GPUs and CPUs today is remarkable and significant, as you can see the given example comparison slide chart. Next, I would like to define what actually is CUDA, or at least remind you. CUDA is a term abbreviation for Compute Unified Device Architecture. It is a parallel computing platform and programming model created by NVIDIA company and implemented by the graphics processing units produced by NVIDIA company. That is an advantage of CUDA, because it is under full control of one company. Of course, in the same time, of course, it is an disadvantage in the same time, because the given technology is locked in by the given company, and no other companies are making the same are producing the same technology. Of course, there exist some competitor solutions, for example, OpenCL, that is more open alternative for CUDA. However, CUDA has a wider application area, at least in data centers and so on, due to better performance and some related terms and features. As I said, CUDA was introduced in the market in the year 2007, and practically every two or in the last time, practically every year, a new version of CUDA and a new version of GPU architecture is appearing in the market. So during the last 6 years, practically every year, nearly every year, a new architecture, a new generation of the given technology is published. But initially, during the first years of CUDA development, that cycle of generation development was 2 or 3 years. By resuming the first overview of CUDA, I could mention that CUDA consists from 2 pieces, from 2 parts. From one side, there is GPU, a hardware technology. From other side, there is CUDA software toolkit, software platform. Of course, only together with technology, with hardware, the CUDA is practically usable. However, theoretically, it's possible to develop any software tool, at least theoretically, also without having an access to CUDA-supported GPU. By looking at the software platform together with hardware capabilities, in the given slide, you can see from what components consists a CUDA parallel computing platform. At the lower level, there are used hardware solutions, GPUs, and the next higher level components are from software side, from software point of view, starting from compiler toolchain. Compiler is based on and tightly coupled with the given operating systems compiler. For example, in Microsoft Windows operating system, the main compiler is Microsoft Visual C compiler, and in the given operating system, CUDA is a plugin for Visual Studio compiler. In Linux operating system, the foundational compiler there is GCC, G++ and GCC compiler, and CUDA is a plugin for the given compiler. In the given slide, you can see that development environment is available also for Macintosh users. Unfortunately, historically, it was possible to use CUDA on Macintosh computers. However, since CUDA 9, version 9, CUDA is not available for macOS systems anymore. If you have an older Macintosh laptop or PC, and you have NVIDIA video card built in the Macintosh computer, you can use, for example, older CUDA version up to version 8. But practically that means that only Linux and Windows is supported by CUDA. And based on the development environment, or based on the compiler toolchain, there are available different higher level libraries coming together, coming in an integrated way together with CUDA toolkit. Of course, not everything is built into the CUDA toolkit. But commonly used libraries, I will make a short overview a bit later of these libraries, are coming together with CUDA installation, and there is not a need to install everything additionally. But not everything is integrated in the CUDA platform. Next slide shows the CUDA software levels. The lowest software level is related to the driver, to the graphics card driver, to the CUDA driver as a part of graphics driver for specific operating system, whether it is Windows or Linux. Driver consists, as it is common for operating systems, consists of user mode and kernel mode parts. That is lowest part of CUDA software, not used directly by software developers and users. From a software development point of view, the common work is based on CUDA toolkit, exposed through CUDA runtime API and CUDA driver API, as well as CUDA functionality is available through different CUDA libraries. CUDA driver API application programming interface is functional level defined through usually C language functions, and that is the lowest level that is available for external software developers. Next, a bit higher level is CUDA runtime level. It is a bit higher. It is a wrapper of CUDA driver API, and that is the usual software component when we are working with CUDA by developing CUDA software from scratch. That is commonly used layer. However, CUDA driver API can be used, for example, when we have an intent to integrate CUDA in any other programming language, not only in C or C++ languages. So CUDA driver API is used for different external language wrappers commonly. That is a common approach there. One of possibilities how to integrate CUDA in other programming languages. But still, CUDA runtime is very low level, and as I said, CUDA libraries are providing a bit higher level functionality, and that is recommended way how to work with CUDA usually in practical life, to try to look at CUDA libraries firstly, and if the given libraries, available libraries, are not providing the necessary functionality, then software developer could look how to work at CUDA runtime level. A very important technical aspect of CUDA is a term named as compute capability. Compute capability describes from CUDA software development point of view, describes the CUDA architecture. So compute capability defines which CUDA architecture generation have to be supported by corresponding CUDA software application. Today, the latest CUDA versions, and as you probably know, the latest CUDA version available currently is CUDA version 11.7. That is the latest version today. And CUDA version number is not directly related to compute capability. So compute capability is the number coupling the hardware side with CUDA software side. And when we are developing any CUDA application, CUDA compiler has a corresponding compiler parameter for compute capability. It is a very important aspect what have to be remembered there by working with CUDA application development. For a purpose of an overview, I have listed there all compute capability numbers starting from version 1.0. But actually, today, the latest CUDA version, for example, 11.7, is not supporting older compute capabilities older than 3.5. That means that older video cards, for example, from the beginning of 2010 are not supported anymore by latest CUDA versions. So 3.5 is practically the oldest compute capability still supported by current CUDA version. And if we have a very relatively old video card, CUDA card, and we want to use CUDA software and to use the given card for software development, then we have to install older CUDA version, which is supporting older compute capability. And that is the reason why in many places still, for example, CUDA 8 is used, because CUDA 8, for example, is supporting compute capability 2.0 or 2.1. So, and as you can see in the given table, practically every new compute capability major number, is corresponding to a new generation of CUDA technology. And the newest technological generation published 2 months ago is Hopper, NVIDIA CUDA Hopper architecture, and corresponding compute capability major number is 9. And when we are providing compute capability number in compiling parameters, in such a way, we are defining for which architecture the given developed software application should work. If we could provide as compiler parameter compute capability 9.0, that means that the given software will work only on Hopper architecture cards, not on older cards. And of course, if we are interested to support CUDA on a wider range of different architecture generations, then we have to provide parameter, for example, starting from 5 or 6 to support Pascal architecture or to support Volta, Turing, and newer generations of CUDA cards. By looking at CUDA GPU product families, on the server side, in data centers, there are used Tesla cards for high performance technical and scientific computing. When we are using CUDA at home, in video games, in computer games, usually we are using GeForce cards that are consumer cards, having graphical output, having video output, and use it for a broad range of tasks at home. And in the middle class, there are categorized Quadro cards. These cards are intended for professional graphics and visualization applications with more higher demand for quality and stability of CUDA functionality. These are 3 groups of CUDA supported product types. Now I will shortly make an overview of GPU architecture. by looking at the basic blocks shortly, from which is consisting any CUDA supported GPU. And I will start with graphics processing cluster. So GPU is consisting of several graphics processing clusters, and GPC shortly is a higher level GPU hardware block containing several subblocks, named as streaming multiprocessors or SMS. Graphics processing cluster, of course, is not supporting only computing capabilities, but the main intent for graphics processor still is to provide computer graphics functionality, and therefore graphics processing cluster contains all the key graphics processing units and subblocks, including rasterization engine and related subblocks there. So, and computing capabilities are only one part of everything what the GPU is providing for the user. As I mentioned, the multiprocessor is a part of graphics processing cluster. And it is a very important part of the GPU, because technically a streaming multiprocessor is running CUDA blocks. It is running, executing CUDA blocks of threads. And each streaming multiprocessor is quite complex unit consisting of at least 32 CUDA processors or cores, in other words. And each core is corresponding to or similar to the core usually known in classical central processing units inside the classical CPUs, at least conceptually similar. Each streaming multiprocessor contains special thread scheduler. I have mentioned there dual warp scheduler. Actual newer architectural generations already provide not only dual scheduler, but already scheduler consisting of 4 separate schedulers. So that is scheduler group already. Each streaming multiprocessor contains a specific cache for storing of constant values. Each streaming multiprocessor is containing local memory for streaming multiprocessor named as shared memory. It is extremely important memory actually for CUDA development, allowing to significantly improve the performance of CUDA applications if used correctly. As well as streaming multiprocessor contains specific subunits for graphics processing, what is out of scope of today's presentation. By looking at a separate CUDA core, at separate CUDA processor, CUDA core has a fully pipelined integer arithmetic logic unit, as well as CUDA core contains floating point unit for processing of 32-bit floating point numbers, as well as there can exist CUDA cores having hardware support for 64-bit floating point numbers. But we have to take into the account that not every CUDA core in the GPU will have both 32 and 64-bit floating point unit support. And in the best case, every 2 cores can contain hardware support for 64-bit floating point unit numbers. That is the reason why, for example, the performance of processing of 64-bit numbers is at least 2 times slower as as processing of single precision floating point numbers, due to the fact that hardware support is limited there for such big numbers. CUDA core is containing also hardware support for logical functions for typical low-level functionality. So every CUDA core conceptually is similar to, as I said, the classical CPU core. Previously, I mentioned also scheduler. So every thread what is executed by CUDA software, every thread is technically executed on hardware side by one CUDA core at any time point. To speed up the execution of threads, there exists hardware support in streaming multiprocessor for scheduling of thread execution. And as I said, the newer CUDA architectures are implementing 4 warp schedulers for in one streaming multiprocessor. And what is warp? What is warp? That is one term related to CUDA technology. Every 32 threads always are grouped in a group called warp. That is specific term for CUDA technology. And that approach that every 32 threads always are grouped into a warp, it is not changing regardless of the generation of CUDA technology, starting from CUDA 1.0 till the latest Hopper architecture, always the grouping is the same. And that means that practically, not technically and physically, actually threads are not executed parallelly always, because the given warps within one warp, threads within one warp actually are executed more or less synchronously. But from a higher level development point of view, of course, we can think that everything is executed strictly in parallel. Due to limited time, I will not take a look at all generations of CUDA technology. I will shortly make an insight into the architecture of Volta and Ampere architectures widely used today, also in scientific and high performance solutions. For example, Volta architecture, commonly based on V100 GPU, contains 80 streaming multiprocessors, and the given GPU contains 5,120 standard precision floating point CUDA cores, providing 15 teraflops performance of standard precision floating point format processing. One new thing since the Volta architecture is introduction of so-named tensor cores, intended for processing of matrices, for 4x4 matrices for machine learning, deep learning tasks. And for that tasks, V100 processor is providing 120 teraflops of tensor core calculations per second. The given V100 GPU supports HBM2 random access memory up to 16 gigabytes, having approximately 900 gigabits per second memory bandwidth. There exists also an option to use GDDR memory, not only HBM2 memory. Each streaming multiprocessor within the given V100 GPU contains 64 cores for single precision processing, 32 cores for double precision floating point numbers, and 64 cores for standard integer number processing. As well as Volta is providing support for mixed precision floating point numbers, what is very important for deep learning tasks. For example, half precision and similar. Any other formats are supported there too. And each streaming multiprocessor contains also 96 kilobytes of shared memory. It looks and it is very small memory, but by taking into account that the given memory is built into the GPU and available for each streaming multiprocessor, it has extremely high bandwidth, and therefore it is, as I said previously, shared memory is very important for CUDA application development. And previous generation before Hopper, what was published this year, currently actual architecture, still very actual architecture, is Ampere with the advanced processor GA102. It has 72 streaming multiprocessors providing 30 teraflops of standard precision processing performance. New thing is from graphics point of view is Ampere is providing already usable support for real-time cinema quality computer graphics. Actually, the given technology appeared one architectural generation ago. It was Turing, but in the Turing architecture, practically it is not very usable for practical tasks. But the given real-time high-quality computer graphics support built in the Ampere already is usable for example, for computer games or other similar tasks. As I said, currently the latest generation of CUDA technology published just 2 months ago is Hopper, intended for usage in scientific applications for data centers, for HPC solutions. And the latest GPU contains already approximately 80 billion transistors. It is extremely complicated GPU device. And rumors there are that in the next months we could wait for consumer version of the Hopper architecture, and it could be named not Hopper but Lovelace. But we'll see whether and when the given architecture will be available for a wider audience, for consumers. So the next, I will shortly make an overview of the principles of CUDA software development, and I will mention the basic terms used in CUDA application development, starting from two common terms as host and device. Host is term for CPU side and its memory, name it as host memory, and device is CUDA term to work with GPU and its memory, and correspondingly GPU memory is named as device memory. So device is an equivalent for GPU and host is an equivalent for CPU. When any CUDA software tool is developed, practically there always is involved CUDA NVCC compiler. NVCC compiler, as I said previously, it is not a standalone compiler. it is always as a plugin for specific operating systems compiler, whether it is GCC in Linux or whether it is Microsoft Visual Studio C compiler in Microsoft Windows operating system. So NVC compiler is a plugin for compilation of device-related software code, and the operating system's native compiler is used for host code related to CPU side. So, and therefore, we are working with an integrated C++ software development, and CUDA actually is an extension to the host software side. If we are working with higher level languages, for example, Python, or for example, usually and commonly Python is just a wrapper of some lower level C++ software application. For example, when we look at PyTorch, when we look at TensorFlow, of course, especially TensorFlow mostly is developed using C++. PyTorch is more Python-oriented and Python-based, but critical parts, of course, are based on C and C++ also in PyTorch. There exists a very good support for Fortran language. That support is not available out of the box by installing CUDA toolkit, but there exists, it is freely available. Not long ago, NVIDIA published, I will write it probably in the chat, new toolkit, name it as NVIDIA HPC toolkit. It is freely available, for example, for Linux operating system, and NVIDIA HPC toolkit contains built-in support for Fortran language, for example. And now I see, Kurt, your question. Sorry, I have not seen it previously. So, do you mean, Kurt, support of ray tracing in a data center, supported card A100? I have to check. I cannot answer exactly to your question currently. It had to be checked. Probably it can be turned off, support on server cards, but consumer cards, GeForce series, all of these series are supporting ray tracing built into the chip. I have to check then that to provide the answer. So, and the next slide shows what I previously said. NVCC compiler is an extension to native compiler used in the given specific operating system. So, and actually, any CUDA software in the end result is hybrid CPU, GPU executable. So GPU part compiled by NVCC and CPU host part compiled by the native CPU supported compiler. When we look at hardware side, hardware component for execution of threads is core. On software side, corresponding part is kernel. So kernel and core, two equivalent parts from hardware and software side. Kernel is a software function called by the host executing on the GPU by any core at any time, specific time moment. as an array of threads in parallel. So kernel is a parallel functional part in CUDA software, and it is a basic component to develop parallel CUDA software. By taking into the account that C and C++ language is the common language for CUDA development, therefore I'm focusing just on the given language. Of course, it is possible to use higher level wrappers, for example, Python, CuPy, or PyCUDA, and so on. But in any case, the knowledge of some knowledge of C or C++ is encourageable by working with CUDA in any case, by working directly with CUDA in any case. CUDA is not introducing any new software language elements, except some new qualifiers shown in the given slide. So CUDA is introducing three new qualifiers: global, device, and host. If any C or C++ function has a qualifier global, that is an instruction for NVCC to compile the given function using NVCC compiler. So that means that a global function will be executed on GPU. Device qualifier also means that the given function should be executed on GPU. However, there is difference between global and device. Global functions always can be called from CPU, only started from CPU side. However, device functions can be called from any global function. So device functions can be called from other GPU functions. That is difference between global and device functions. And host is by default, that is common function called from any CPU functions. Host alone is not mandatory to use, but host can be used together with device qualifier. But if any function is defined as host and device, that is instruction for the compiler to compile two versions, one version for CPU and one version for the host. So, and therefore kernel is a way how to translate any common sequential code into parallel code, how to unroll any, for example, classical sequential loop into parallel execution approach. And practically every kernel on the hardware side is executed as a thread. And as I said, at any time moment, kernel is executed as a thread on a specific CUDA core. It is important, very important part that there are used not only threads, but threads are grouped into blocks. It is a foundational part of CUDA. So threads are grouped into blocks, and practically, physically, at any time moment, one block is executed by a specific streaming multiprocessor on the hardware side. Important thing is that threads within a given block can easily cooperate with other threads. And the support for coordination and cooperation is very well hardware supported. Therefore, the cooperation is lightweight and very well synchronized. Each block has an unique identifier available as a built-in CUDA variable. It is named as block IDX. And by looking at threads, every thread has an unique identifier as a built-in variable thread IDX. And thread IDX is unique for specific block. If we have multiple blocks within each block, the numbering of threads will repeat. But of course, the thread IDX is related only to specific block where the thread is located. And blocks are grouped into a grid. And grid is a logical concept corresponding to the GPU as a whole hardware system. So, and logically, blocks and grids are three-dimensional structures. If GPU practically, of course, is one-dimensional or two-dimensional hardware system. But when we are developing CUDA software, we can conceptually think about a three-dimensional structure, but is very well appropriated, for example, for different physical simulations in 3 or 2 or probably 1 dimension. So grid and blocks are concepts, logical concepts as three-dimensional data structures. And actually block IDX and thread IDX have three components, three fields, X, Y, and Z. If we want, we can skip Y and Z. We can use just one dimension and work as with one-dimensional structure. And the next slide shows the way when we are looking at the grid and at the block as a two-dimensional structure. So every block, as I said, has built-in identifier block IDX, and every thread within a block has an identifier thread IDX. And we have to remember that the structure is uniform. That means that if we define 10 blocks and 8 threads per block, that means that every block will always contain the same number of threads. It is not possible to run CUDA software. It is not possible to define different number of threads for each block. So the structure is fully uniform, always fully uniform. And additionally, every thread can execute the same kernel. It is not possible to run different kernels on different CUDA cores. So that is a significant difference in comparison to CPU, when we can freely run different threads with different tasks. That is not possible at CUDA side. So when we are running one software kernel, the given kernel will use everything that is available on the GPU side, and we cannot commonly, most of cases, we cannot freely run several kernels at the same time on one GPU. Of course, starting from Ampere generation, there is a new concept for multiple instances of CUDA in the same time. That is intended for usage in virtual environments where different users are working with graphical units, graphical processing units. And therefore, that is a new concept where it is possible for different users to run different kernels at the same time. But for one user, usually only one kernel can be executed at any given time. It is possible to improve the performance by providing concurrent data copying from copy operations from host to device and in opposite direction in the same time when the kernel is executed. But that is not fully parallel approach. That is concurrent, but not parallel. So, as I said, thread blocks allow an efficient cooperation within the thread block. It is possible to share shared memory between threads within a block. And usage of threads allows scalability. By increasing the number of blocks, it is possible to run or increasing or changing the number of blocks. It is possible to run any CUDA software on different available CUDA resources. By resuming the execution process of CUDA kernels, each thread is executed by one GPU core. each CUDA block is executed by one streaming multiprocessor. And it is not possible to have a situation where any CUDA block is split between several streaming multiprocessors. Only one streaming multiprocessor will execute one block. However, one multiprocessor can process several concurrent blocks. That is a normal situation, but one block cannot be split between several multiprocessors. And each kernel is executed on one device. If we have several GPUs, it is not possible to execute one kernel on several devices at the same time. That is practically more or less manual process to support multi-GPU development. That is task for software developer to develop a CUDA application which could efficiently use all the GPUs that could be available for execution. And the given slide is repeating what I said previously. Every 32 threads always are grouped into a warp. It is a technical concept. It is not possible to change anything there. We can take into account only that term. And it is possible to take into account that term also very efficiently by knowing that practically these 32 threads will be executed always synchronously under the hood. And by knowing that fact, sometimes it is possible to implement different software tricks, how to organize and how to implement synchronization between threads by not using any higher level concepts as mutexes and so on. And by finishing the short overview of CUDA software principles, I will remind you that the work with CUDA consists of three simple data processing steps. Firstly, all the data for CUDA data processing always firstly have to be prepared on the device side. So CUDA can normally work only with the data available on the GPU side. Probably it could be video card. Of course, it is initially a video card memory, or in other words, global memory. So the first step always is to copy input data from CPU side to GPU side. Of course, to be correct, the latest CUDA versions are supporting a new concept name it as CUDA unified memory. And by using that concept, it is not obligatory always for the software developer to manually copy anything. It is possible to use that concept, and unified memory driver will automatically copy all the data between host and device or back. But still, in any case, unified memory, it will do that automatically instead of any manual work. But if needed, it is still possible to manually copy the data. So from CPU to GPU side. The second step actually is execution of CUDA kernel, the parallel code. All the data already is available on the GPU side. And the last step is when the processing has been finished, the results have to be copied back to host memory, because CPU cannot access directly anything what is located on GPU side. So everything have to be put it back to the CPU memory before use the obtained results. And now I will shortly look at memory types, not going into all the memory types what GPU has due to the limited time. But there you can see what components are related to the GPU memory. GPU memory is split into two main parts. GPU memory located on the video card or graphics card, that is global memory, and some part of memory built into the GPU. It is cache memory, not controllable by software developer in any way. It is constant and texture caches, and shared memory as well as register memory for each multiprocessor. Global memory located on video card outside of GPU actually is divided into several subparts. Global memory is part of random access memory available for normal usage where to store data. There is one part, it is local memory, one part on physically located on random access memory chip or chips. It is local memory where GPU will store any variables which are not possible to store in the registers as a temporary memory. Constant memory where any constants can be stored. And texture memory. Texture memory, specific part of memory which have corresponding cache in the GPU side. And due to the limited time, I will look only at global memory, more or less. But there I have defined what texture memory is. As you see, texture memory is accessed by using texture specific texture, CUDA texture instructions, and it is similar to constant memory. So I have not mentioned there what is constant memory, but as the name shows, constant memory is used for storage of variables that are just readable for CUDA software, not readable, not writable, just readable. Texture memory is similar, but there are available specific CUDA functions allowing to access texture memory based on principles coming from computer graphics. Using specific texture access functions. For example, there is a support for value scaling, for value clipping, for processing at the borders of any data set, and so on. So texture access allows to automatically at hardware level to scale values, as well as to process any border cases when usually we could have out of bounds issues otherwise. Shared memory, I have mentioned previously, it is built in the GPU chip. In each streaming multiprocessor, there is available shared memory. Usually it is no more than 64 kilobytes, but in newer Ampere cards, it is already at least 96 kilobytes. And host memory that refers to CPU side. I not repeat everything what is related to CPU side, and host memory is managed by using C functions, malloc or free, and new or delete. And corresponding equivalent on GPU side is global memory. It is the main abstraction by which CUDA kernels read or write device memory. Device memory is defined in the device address space, and actually device address space is unified with host address space, and that means that software developer have not to think directly about any separation between device or host memory. But of course, it is not allowed to use, for example, any variable allocated on device memory side to use directly in host functions. And we could obtain bad results in the best case by using that, by doing that. As I said, logically, CUDA grid is a three-dimensional structure, and therefore, when we are using, for example, 2 or 3 dimensions of CUDA logical structure, we have to transform these identifiers, block identifier fields, we have to transform to index used to index our actual data sets. For example, there is shown a pattern, common pattern, how to compute an index for one-dimensional data array, because usually, at least by using C language, all the arrays in most cases are defined adjusted as one-dimensional data arrays. And when we are using, for example, three-dimensional block indices or grid indices, thread indices, then we have to transform these dimensions to, for example, to one-dimensional index, and there is shown the pattern. If we are just using one dimension, then the transformation is very, very simple. Actually, no transformation at all. But if you use, for example, block IDX point X and block IDX point Y fields, or all three dimensions, then a corresponding transformation is needed there. And there shortly shown approach how we can index one-dimensional data by using built-in in the CUDA environment built-in variables thread IDX, block IDX, and block D. So it is clear thread IDX is a unique index of thread within a block. Block IDX is unique index of a block within a grid. And block dimension is built-in CUDA variable available in the kernel, containing a value how large number of threads are defined per each block. That is block dim. And due to the fact that thread IDX, block IDX, and block dimensions can be handled not only in one but also in 2 or 3 dimensions. Therefore, these actually are data structures having 3 fields. And by default, all these fields have value 1. On block dim, by default, have all these fields valued as 0. And in the middle, there is shown excerpt how to use 2 dimensions by defining block size as consisting of 8 threads in X dimension, 8 threads in Y dimension, and 1 thread in Z dimension. And so block size, grid size, so we'll define how many blocks in each dimension will be used. And question is how the kernel knows how large is block dimension. Kernel knows the block dimension and grid dimension due to the fact that these parameters meters have to be passed to the kernel when the kernel is called from the CPU. As you can see in the middle, for example, if I have some hypothetical kernel, name it as my kernel, in these 3 caveats are placed. The first is grid size, and the second parameter is block size, number of threads per block. And in the caveats are following any actual kernel parameters. In the case of usage of all 3 dimensions, of course, the indexing is a bit more complicated. Probably question could be why we could need several dimensions. It is related to the fact that the number of maximum size in one dimension is limited. For example, number of threads per block usually is limited to 1024 threads per block in each dimension. So that means that we cannot define very large blocks. In any case, in practical life, we have to use also blocks due to the fact that number of threads per block is limited. And also the block size, so number of blocks in each dimension is limited. X dimension has larger limits. It is 2 in power 32, quite large limit, but still limited. And to make possibility to work with extremely large number of blocks, then we can use together with X, we can use together also Y and Z dimension. So usually that is one of reasons why we are using not only one logical dimension, but several. That is very short overview of CUDA technology, and I will continue with a very short insight into the CUDA support for machine and deep learning tasks by looking at some basic libraries coming together with CUDA or external libraries. But I still will start with a look at GPU hardware. And previously already shortly mentioned that starting with Volta architecture, GPUs have a built-in support for computing of matrix operations. And common matrix operation for deep learning tasks is multiplication of two matrices. And supporting hardware technology unit there is named as Tensor Cores. Tensor Cores is a hardware block in each streaming multiprocessor, providing work in parallel at hardware level with mixed precision 4x4 matrices. If we have larger matrices, actually the larger matrix is splitted into the subblocks, resulting in 4x4 matrices. And so large matrix is calculated based on splitting into smaller matrices. Additionally, very important part is mixed precision support, because matrix multiplication is related to usage of 16-bit floating point numbers or 32-bit floating point numbers. And Tensor Cores is using matrix multiply accumulate MMA approach. So by using, for example, half precision floating point numbers, actually the result precision is not lost at all, because matrix multiply accumulate internally is using higher precision, and as a result is rounded down to the necessary precision. And additionally, CUDA hardware supports these matrix multiply accumulate operations up to 256 elements by looking at 3 dimensions. So not only that is one thing there. Support for multiplication and addition of matrices. Not only multiplication, but also addition is this additional component there. For example, the next library, what I will mention there, cuDNN, under the hood actively is using Tensor Cores where available, if available in practice. Starting from the Ampere generation, interesting thing there is the support for several new floating point and integer types. For example, one promising type is tensor format, tensor floating point numbers, shortly TF, as well as BF. BF, probably you know, is from brain floating point. That is format invented by Google company. Therefore, that is reason why it is named as brain floating point. Every of these formats has their own advantages, but TF is promising because it is relatively well compatible with classical floating point FP32, and there we can see the comparison of performance using different floating point types. But it is clear, if possible, it is encourageable to use in deep learning tasks. It is encourageable usually to use half precision floating point numbers due to very good performance. As I mentioned previously, CUDA has different support for different libraries, and several libraries are installed together with CUDA. But the larger collection, not everything coming together with CUDA installation, is named as CUDA-X. CUDA-X is a common term. It is a collection of CUDA libraries, tools, and technologies that deliver high performance across multiple application domains. CUDA-X is just a collection, it is not something installable. It is just collection, just a list of all CUDA libraries. For example, mathematical libraries, one part of these mathematical libraries are coming together with the CUDA installation, including cuBLAS, cuFFT, cuRAND, cuSPARSE. Several libraries there are available as separately installable libraries. For example, Trust actually is an open source third-party C++ library, but coming together also with CUDA installation. CUDA-X contains also the libraries for image and video processing, for communication between GPUs in multi-GPU environment. CUDA-X is listing also libraries for deep learning, including cuDNN, what I will mention a bit later today. For deep learning, cuBLAS, one of CUDA mathematical libraries, cuBLAS, it is practically foundation for deep learning solutions today. For example, PyTorch and TensorFlow cannot be efficient if could not use cuBLAS. So, but by principles, cuBLAS is CUDA implementation of classical BLAS, basic linear algebra subprograms library, very well known since beginning of 1990s. cuBLAS practically is exposing all the same functions. So if anyone has experience with BLAS, it could be not a big problem to use cuBLAS, because practically all these same functions at 3 levels: for vector operations, for matrix vector operations, and for matrix operations. And for example, GAMM, it is a foundational block for many deep learning tasks where matrix multiplication is needed. So cuBLAS from API usage point of view provides the same functionality. Of course, everything is based on CUDA. So every function there is parallelized and GPU supported. cuBLAS supports 4 data types, including single precision float, double precision, complex and double complex numbers. And every BLAS function has a cryptic name, but from these characters there we can know what functionality is supported. And small difference, technical difference, is that all cuBLAS functions have a prefix cuBLAS. So, and for example, GAMM means SGAMM means that is for single precision data type. GA means it is general, and MM means matrix multiplication of matrices. So next, very shortly, one library, relatively new library coming as a part of CUDA X tool list is cuSOLVER. cuSOLVER is GPU accelerated library for linear algebraic system solutions, for dense as well for sparse matrices. It is a higher level package based on previously mentioned cuBLAS, and another library not mentioned today in more details. It is cuSPARSE for working with sparse matrices. And given cuSOLVER can be used for machine learning tasks, and that is reason I have mentioned there to solve linear systems of equations and similar tasks. Another library, cuRAND, is library for generation of pseudo and quasi-random numbers using GPU. cuRAND provides two parts. One is for usage on host side, on CPU side, and another part is for usage on device side. For example, if we have CUDA kernel and we want within the kernel generate any random numbers, we can use the given device side, device support. Host side is intended to use when we, for example, have a task to generate large number of random numbers and to use later these numbers in any CPU based task. Then we can use the first part of cuRAND. Due to the time limit, I will not go in any details about cuRAND. cuTENSOR, as the name shows, is a GPU accelerated tensor linear algebra library, which is providing tensor contraction, for example, reduction and element-wise operations. So it is a library for working with tensors, with multidimensional matrices, providing mixed precision support, providing direct, that means without need to copy any data between host and device, direct tensor contractions, reductions, element-wise operations. And cuTENSOR is supporting up to 64 dimensions of tensors. Another that is not so cuTENSOR is relatively low-level library. So, and by going further, next shortly I will mention TensorRT. It is higher-level solution intended for inference tasks. And it is built on cuDNN and cuBLAS libraries, allowing to optimize, for example, neural network models trained in different major well-known frameworks to calibrate for lower precision with high accuracy and to deploy to hyperscale data centers and so on. So for inference, for usage with previously trained models, we can look at TensorRT technology. And TensorRT is providing application programming interface, for example, to import pre-trained deep neural network models from PyTorch or from TensorFlow, and to optimize these pre-trained models to use efficiently on GPU side. And for example, TensorRT is supporting ONX6 technology as a format for exchange of deep neural networks or deep machine learning models. So that is a bit higher level technology. Of course, usage of CUDA on one GPU is just one part by working with CUDA. In more complex solutions on server side, in data centers, usually we have to work with multi-GPU solutions. And in that case, usually we have to involve also, for example, MPI, message processing interface to provide communication between different nodes in multi-GPU environment. If we are working with one node in the last time, there is available technology providing capability to efficiently transfer data between several GPUs within one node. It is technology NVLink, acting as a high-speed interconnection technology, firstly introduced 6 years ago in Pascal GPU. When we are working with one node, it is efficient way if the hardware motherboard is supporting NVLink bus. And currently, the NVLink is evolved to the third generation, used together with Ampere A100 GPUs, with increased the number of link speed and bandwidth. And there is introduced also NV switch technology. It is something like InfiniBand and Ethernet technologies for low-level data transfer between GPUs. Not just within one motherboard but for between several motherboards. And the newest thing built into the Ampere GPUs is multiple instance GPU support, MIG, which is newly added in the A100 GPU, allowing a single GPU to be managed and utilized as a multiple virtual GPU. So it is very important thing for virtualized containerized solutions, where each virtual GPU is called as an instance, and each instance streaming multiprocessor is occupying separate and isolated data or control paths and memory areas. That is typical issue how to efficiently use CUDA based on older GPUs, but starting from A100, the new approach, MIG, is promising approach to efficiently use CUDA and GPU hardware for multi-user environment. Now I will take a look into one important library, and together with cuBLAS, cuDNN is a foundational block of practically of every today's framework used for deep learning or machine learning tasks, especially for deep learning. So cuDNN is intended for deep neural network lab support. So it is a deep neural network library, or shortly cuDNN. cuDNN is a GPU accelerated library of primitives for deep neural networks. It is not coming together with CUDA installation, but it is freely available as a separately installable tool framework. And as I said, practically PyTorch, TensorFlow, Chainer, MXNet, all popular neural network libraries for GPU acceleration are using cuDNN. So that is a vital part of any advanced deep neural network library today. What cuDNN is providing? What are the main features of cuDNN? cuDNN provides functions for convolution support, both forward or backward, including cross-correlation. cuDNN is implementing a large number of different algorithms, and good thing is that cuDNN is able automatically to choose a most appropriate algorithm for forward or backward pass based on the input data. That is one thing there, that the user have not obligatory to manually choose which algorithm to use. One thing what can make an influence on the choice of specific algorithm, for example, is the availability of the necessary GPU memory. Because every algorithm has their advantages or drawbacks, and one parameter there is the available memory. cuDNN provides functions for pooling, for calculation of activations, for softmax, arithmetical, as well as tensor transformation functions. So practically, typical building blocks for convolutional neural networks are built into the cuDNN, and I have not seen any framework what could implement the given functionality from scratch what cuDNN is providing there. So as I said, cuDNN is used in the background practically by most popular high-level neural network libraries today, including, of course, top two, PyTorch and TensorFlow, but as well as other Caffe2, which is a part of PyTorch today, as well as Microsoft Cognitive Toolkit, MXNet, Paddle, China library made in China, and so on. In the next slide, you can see the structure of cuDNN. cuDNN for the developer provides an API, application programming interface, where it is possible to choose a necessary function. Actually, cuDNN is quite complex library, and it is not intended for wide audience. Actually, it is a low-level library with very large number of different functions. But if we'll have some time, I will show you one example today, how to use cuDNN in practice from scratch without any external dependencies there. And actually, by starting to work with cuDNN directly, it is not so difficult. But of course, in PyTorch, that the same task could be some lines of code instead of several files. At lowest level, cuDNN is providing implementation of different algorithms for gradient search, for forward backward passes, for pooling activations, and so on. Some algorithms are based on dynamic approach, where at runtime the algorithm is compiled to the executable code at runtime. Therefore, there is static as well as dynamic part of CUDA. And I have not previously mentioned, but actually CUDA has a dynamic compiler allowing to compile code on the fly during the runtime execution. And for example, many Python wrappers are using that runtime CUDA compiler. It is named as NVRTC, what you can see there at the bottom in the CUDA runtime compilation block. NVRTC compiler is freely available, and it allows to execute any CUDA kernel by compiling C++ code on the fly. And it is not necessary obligatory to compile only statically before the execution. And for example, several Python wrappers of CUDA are implementing the given approach. cuDNN library exposes a host API, but of course everything at the end is executed on the GPU. For different data types, there are used specific descriptors, handles. For example, for tensors, for weights or filters, and so on. For everything, there is used appropriate descriptor before we can use cuDNN for actual computations. cuDNN provides support for n-dimensional tensors with maximum dimensions up to 8-dimensional tensors. With additional parameters as padding, stride, and so on, what is needed for the work with deep neural networks. It is possible to use different storage formats for tensors there. It's possible to work with 4-dimensional, with 5-dimensional tensors, for example. And the storage layout is defined by characters, for example, NCHW or NCDHW, representing batch size, number of feature maps, depth, height, and width, for example, of the tensor. One small example there, by considering that we have batch of data sets, for example, images, in 4 dimensions with the following dimensions. For example, one is batch, could be batch size, C 64, 8, height 5, and width 4. And by using a specific storage format, for example, NCHW, we can there see how the data could be stored accordingly in the memory as one-dimensional array fact in practice in the background. So there are different functions and different possible storage formats what could be more appropriate for different tasks. Of course, for convolution neural networks, one important task is convolution process, or technically it is usually it is cross-correlation. Corresponding function there is cuDNN convolution forward. I will not go in any details because we don't have time enough, and the library is quite complex. One thing what could be mentioned there is that in comparison to working with CPU, there one limiting and thing what have to be taken into the account is that before we can use cuDNN functions for processing of tensors, we have to prepare the necessary space in the memory, and it is named as workspace. So you can see there is a parameter workspace. That is a amount of memory that have been allocated before we have starting to use specific neural network functionality. So firstly, we have to allocate memory big enough to be sure that all the data for tensor processing will fit within the given memory area. And that is limiting factor because if the batch size, for example, is large, or if the number of dimensions is large, of course, it is very easy to go out of bounds. Practically, that is one of most difficult and trickiest parts by working with GPU-supported machine learning tasks, how to efficiently use memory and how to split large tasks, large data sets into smaller subsets to be possible to use the available GPU memory. both for forward as well for backward pass, there can be used different algorithms. And as I said, cuDNN is able to automatically to choose appropriate algorithm. If, of course, it is possible to choose fully manually any usable algorithm, but the point of cuDNN is to provide automatical usage of any most appropriate algorithm as a compromise between performance and memory usage. For backward pass, there are three functions for backward gradient calculation of biases, of weights or filters, as well as for actual data. So we can see that these functions are quite complex with multiple parameters, because I have skipped all these functions are calculating not only just convolution forward or backward, but also are providing additional parameters alpha and beta for scaling of results. So that is also additional reason why the number of parameters is so large. And the given slide summarizes the reason why different algorithms are there implemented and available, because of course each of the algorithms has their own advantages or drawbacks regarding the necessary memory amount or performance. There exist also several attempts from different made by different researchers and specialists to improve the work with cuDNN by splitting batches into smaller parts. So, for example, one scientific source, what is mentioned there, proposes approach named as micro cuDNN, splitting batches into micro batches into smaller parts and to improve the overall performance there. And now I will go through some slides to show how to start to use cuDNN if necessary. Of course, if you are working with some experimental solutions, if you are working with scientific tasks, it is not viable option to use cuDNN directly. But my opinion is that cuDNN direct usage could be available option, for example, in commercial client-side applications where, for example, Python could not be appropriate solution, where everything could be compiled as a binary code to hide the know-how, to hide the implementation details, for example. For that purposes, direct usage of cuDNN or a compiled approach could be appropriate. Of course, PyTorch and TensorFlow in most of cases, practically in 99% of cases, is fully appropriate way how to work with deep learning tasks. But my goal there was to show you what is used under the hood. So there I have several slides to show how we can use cuDNN, how we can start to use cuDNN. Firstly, we have to initialize GPU. Firstly, we have to, for example, to estimate, to get the number of available GPUs in our system. Next, we can read the device properties to exactly know what are the capabilities of the available GPU. Next is the starting of cuDNN, but defining the necessary descriptors. For example, there you can see cuTENSOR descriptor, and we are creating tensor descriptor. Then we are proving at the last line, we are setting the parameters for tensor, defining it as 4-dimensional tensor, and providing parameters n, c, h, and w. Next, we could allocate some memory on GPU side, and there you can see call of CUDA function CUDA managed. And cuDNN managed means that it will use unified memory. So, and we don't need to manually copy data between host and CPU by using unified memory. Next, in the given sample example, I'm creating activation by using sigmoid function. So, so activation mode cuDNN activation sigmoid is a built-in constant defining which activation function to use. It is possible, for example, to use ReLU instead and several other functions. And the example is finishing with the call of cuDNN activation forward, just to try the activation. It is very short example without any actual neural network. Actually, I have prepared also practical example. So we have 12 minutes left. At the end, I will show you in practice how cuDNN can be used, for example, to create and to use, for example, a ResNet neural network created from scratch with cuDNN. And at the end of my presentation of overview, I wish to show you an insight, to provide an insight into the very promising and very interesting, I think, library. It is Rapids AI library. It is open source library. It is not directly related to CUDA. It is separate third-party library. But in the same time, it is fully based on CUDA GPU technology. So every functionality provided by Rapids is accelerated by CUDA. So Rapids is a suite of open source software libraries and Python, Java application programming interfaces with the ability to execute end-to-end data science and analytics tasks, pipelines entirely on GPUs. And everything, every function is utilizing CUDA for low-level compute optimization, execution, exposing GPU parallelism and high bandwidth memory speed. That is so, and the user can work with Python without interesting about CUDA directly. The initial idea of Rapids framework is based on classical ATL approach. As you know, it is extract, transform, and load concept. So Rapids implements the given concept in modern way with very, very good performance. Rapids was not created from scratch fully because it is using concepts and implementation of the well-known Apache Arrow project. It is project library for data storage and data processing in columnar format. So Rapids is continuing the traditions, starting with a very well-known Hadoop framework. However, everything is running on GPU side without unnecessary data transferring between host and GPU. Rapids has three main components. One is QDF, QML, and QGraph. And there we can see integration possibilities also with different other libraries, including cuDNN and deep learning frameworks such as PyTorch or TensorFlow. At the basic level, Rapids is based, of course, on cuDX, cuBLAS, and other related libraries. But for programmers, the API mainly is Python. One of the main components, QDF, is GPU data frame library for loading, joining, and aggregating, file filtering, and other manipulating of data. As I said, it is based on Apache Arrow format. And as well, I would like to mention that cuDF is similar in practical work. It is similar to the work with Pandas Python library. So if we have previously worked with data frames using classical Python libraries, then API there is very similar. Another part is QML. It is GPU machine learning algorithms suite, a set of libraries that implement machine learning algorithms and mathematical primitives, functions sharing compatible APIs with other Rapids projects. Every function there is supported by CUDA, accelerated by CUDA, providing different machine learning functions, including clustering, for example, k-means, dimensional reduction functions, also linear models of regression or classification. Different algorithms there are implemented and available, as well as non-linear models for regression and classification, different preprocessing algorithms. For example, for time series processing, classical Holt-Winters exponential smoothing model is available there, accelerated by CUDA. And several different other algorithms are implemented there with Python interface. So if you have tasks where the given algorithms could be used, then I can recommend to look at Rapids QML library. And the third main component is cuGraph. It is a GPU accelerated graph analytics library. It is a collection of GPU accelerated graph algorithms providing functionality for calculation of centrality, community, and different other graph related things. And at the end of my presentation there, one side component or foundational component there is a Rapids Memory Manager. And it is well known that GPU-based computing has limitations and drawbacks related to efficient memory management. And many toolkits and many frameworks are trying to use and implement their own memory management functions. For example, if we look at the source code of PyTorch, we can see also that PyTorch is using their own memory manager for GPU data processing. But in my opinion, promising solution there is Rapids Memory Manager because it is used by Rapids, but in the same time it is usable also separately at different other tasks and places. It is a package enabling to allocate device memory in a highly configurable and efficient way, providing different types of memory management and allowing to improve the efficiency during the work with large amount of different data types and small chunks of memory. It is common issue with CUDA, for example, and difficulty, and Rapids Memory Manager can efficiently or partially solve the given issue. And at the end, we have 4 minutes left, and therefore I will shortly show you one practical example. I will switch my screen to my development environment. If you have any questions, don't hesitate to ask. So I will share my whole screen. So I hope you can see my screen. Now I will put in my development environment. So I have prepared one example. First one is actually 2 examples. First one is basic example what I showed you to present how to start to work with cuDNN from scratch. So I hope you can see. I cannot switch to full screen mode. So what was shown in the slides is practically available there in one piece. So just a demo example how to try to work with cuDNN to define activation function, just activation function. So I'll try again to make larger everything there. However, I don't see possibility to increase the size. Ah, okay, toggle full screen. But however, not big difference there. So and I will try to run the given example. So, and the given example is very simple, just creating input array and output array, which is calculated based on activation function sigmoid. And in at any moment, activation function is possible to change, and there you can see which activation function types are supported by cuDNN, including practically common types, ReLU and other similar commonly used activation functions are built in the cuDNN. For example, I can try to switch to ReLU activation. But just by changing the constant, I have switched to another activation function. So, and by using ReLU, I have the same output as input. And another example is more complex. It is already fully implementing ResNet 50 algorithm. ResNet algorithm, and I will shortly show you we have already time finished. It has classical ResNet algorithm, 5 layers, including convolution, activation, pooling, padding, and batch normalization layers. Everything is based on cuDNN, no external dependencies there. And now if I run the given example, firstly by compiling, it will compile. So, and now I hope you can see everything. It is running, training, accuracy is increasing, improving, and at the end, based on MNIST dataset, so 60,000 images for training and 10,000 images for testing. Classical dataset, as you know, is used there. And everything is running on my local machine currently. So, and ResNet accuracy for my test dataset, MNIST dataset is, as you see, 96.9%. And everything is created using only cuDNN wrapped in objects, layers, wrapping all the low-level cuDNN functionality there. So that is a real example, but in the same time not very complex. So the time is over, and I would tell you thanks a lot about participation today. Thank you for participating. And if you have any questions, please ask me. So thank you. That's all. And if no questions, then thank you again and goodbye.